but the important part is that it's kind of syllabic.
All fired up.
Not all L's syllabic, but all syllabic L's have to be correct.
No, there is no markers.
So the L is the bigger category, and then syllabic L is subcategory.
So markers you need.
Oh, I have, yes. Yes, I do. Right. Blue, brown, red, black, and the eraser? Yes, I do. Oh, multiple erasers. Yeah.
And I can
Let's actually. And I'm going to want to volunteer for next Friday, next Thursday for a paper that I haven't even put up yet. So let me actually put that up once I've got a volunteer for other papers. Well, I guess we do have volunteers for other papers. Not for stuff that I was going to have for next Thursday. Let's see. I want to do another debugging paper next Thursday, and potentially an automated repair paper the Tuesday after that. But it's still not up on the schedule. So I will discreetly put that up.
So when the second round of presentations start,
Which is next week.
Yeah, do we have very quickly for them as well?
Yes.
So
But one critique a week isn't too bad. And that way it's a smoothing function, right?
okay.
Okay,
Sure.
Like this, doing the numbers.
Are we missing two?
Yeah.
3.
I mean, the lecture is going on, so you
Yeah.
better be here.
Might as well go.
So today we are going to talk about concolic fault abstraction. First, we will have a brief introduction and an overview over the previous work. Then we will see how the algorithm works, and we will have more detail on the part called error trace construction, and at the end we will have the evaluation part. So one important part of debugging is fault localization, finding the cause of the error, right? So there are two types of techniques that try to solve this problem. In type 1, we compare failing and passing runs, which, so we have a program P, and we have a bunch of test cases in T, and then we run this program on all these test cases, and we will have two sets, passing ones and failing ones, right? So how it works, they say that, for example, instruction 1 was mostly executed in the test cases that we failed on, but not in the passing ones. So it is probably faulty. So that's how they try to detect the fault, right? So either they will at the end say this single instruction was a fault, or they rank the instruction through some probability formulas that they have, right? So another type 2, is the ones that they have a static analysis of error traces. So first we want to know what are the error traces, right? So we have a program, and we have a single test case T. If we run T on P, it fails, right? So it will give us an execution trace that has failed. We call this an error trace. So so there's something called error trace formula. And I want to talk about it right now and see what it is. It is kind of a formal presentation of the error trace, right? and it is consists of three parts: an initialization part, conditions, and an assertion. So what they say is that in the initial part they put all the constraints on the argument. So if you want to have an example, say we have a function named UI, which takes two arguments, start and end. And then in the body of the function we have, for example, if some condition, then assert, right? Assert something. So if you wanna write the error trace formula for this one, say the test case is like 3 for start, 4 for end, right? So the initial part will be the start equal to 3 and end equal to 4, right? So this is the initial part. And then they have the condition, which kind of summarizes what has happened in the program. In this case, it's very simple, and we will put C, which kind of says what test we have executed in the program, and then they will put the assertion here. So if the program fails, this formula is unsatisfiable, right? So what they do is that they give this formula to a solver, and they say, and they ask the solver to kind of solve it and make it satisfiable, for example. So the solver tries and say, okay, if we select this condition C here, this will be satisfiable. So maybe the fault was in C, and that's how they try to figure out what the fault was, right? So now we want to see what was the problem with these two types, right? So the first one, as we can guess, is like we are running so many test cases in one program, and our test cases should have a, oh, sorry. Okay. Our test cases should have like a high coverage, like covering all the program, right? Otherwise, we may not find a fault at all because it's not even executed. So it makes a limitation, right? So what's the problem with the static ones? So as we can guess again, it's like the error trace may get too big, and then we want to use the solver, and it's so expensive. It takes a lot of time for it to find the right condition to flip, right? And also we are using complex mathematical models, and yeah, that's why it is like it has a weak scalability. So that's why we are moving forward with this new approach, which kind of combines both of these, and it is called concolic fault abstraction. So it is a combination of a concrete execution and symbolic reasoning, and it is kind of both dynamic and static. So one contribution of this paper is that it tries to solve the problem that what happens if the trace is too big, right? So what they do is that they try to split this trace into subtraces and then give those subtraces to the solvers. That takes less time because they are smaller. So their contribution is that they explain how they split the traces and how they put back the results all together. And also they explain how they how they solve the complexity of like dealing with pointers. So yeah. Any questions for now? Okay. So now we want to see how their algorithm works, right? So first what they do is that they generate the error trace. So we talked about error trace, right? So what they do is that they instrument the program to kind of, so like we have this program P, and they instrument it somehow that the result is an executable file that have the error trace sigma, and it is executable, right? So they instrument all the header files and all the prototypes necessary so to make it executable. So yeah, so in their case, they were doing the experiment on a program that had an injection fault, and the results they got from the error trace consisted like 976 lines with like 89 function calls. So like finding the bug in 1,000 lines kind of hard, right? So we need something more. So they will try to analyze this error trace here to make it smaller. And yeah, and that's like one of the algorithms they use in their approach. So they use like two types of techniques. One of them is address sensitive. The other one is address insensitive. So now we want to take a look at the example and go through the example. So this is a faulty program that they have, which has a injection fault in it, right? So what happens here is that we have this function main. It calls two functions, right? Compile file and read file. So through a chain, this compile file leads to something, to call to a function called compile address here. Here is an injected fault. It says if the program is faulty, call compile regex. So what happens in there is that
It's opposite. The
Okay,
problem is
opposite?
not faulty.
okay, so kinda we have a global variable up there which is last regex, right? So if the program is faulty, somehow the last regex stays uninitialized. So here, if we have last regex and uninitialized, right? And okay, and if we go through this function call, we will get into something, some function called research. So here research is using this variable rxb, which it kind of points to the same thing that last regex is. So because it was null here, we will have segmentation fault, right? So rgx null. Fault. So that's our example. Now we want to see how the approach works for analyzing the error trace. So as I said before, we have two types, address insensitive and address sensitive. So in address insensitive approach, we want to see why a particular value pointed to a particular had a particular value. Here we are not talking about pointers and memory locations, right? So as you see, it says, okay, last regex was null, was 0 at the beginning, and then they'll see, okay, where did we use it? In address regex, and then they continue it, and they'll get into RxB, right? So we kind of see what has happened here, but kind of this information is not enough to like debug it, because it only has the chain of like using variables, but you don't give us the information that why did, for example, address regex point to the location that it did. So we want to have that information as well. That's what happens in the other figure. Which, as you see,
So let's actually go back to the shorter figure just for a second and try to think about what that captures. So what was your explanation of what that was capturing?
chain of using the variables, like the values that have been used.
Sure. Sure. So in terms of now the audience, what is your interpretation at a high level of that?
Well, we see where the variable was assigned and or not assigned and where it was used.
Sure. Sure. So it's flow of a buggy value or potentially buggy value through the program in some way. Is that what does that tell you then? Let's say that your failure is that you observe a segmentation fault, which we do. What is this telling us?
Where the segmentation fault is stemming from?
Essentially, or it says why the failure occurred, in a sense, at a high level, right?
Okay. So if we go to the other one, as we see, we still have line 3, which is last digit equals 0, and we still have line 42, which is the same thing here. So what happened in between? So we are also trying to keep track of the pointers, like what pointed to what. So like my explanation is that here in line 42, they said that, okay, we want to know what is in the variable address. So they go and see, okay, address is pointing to something called car_CMD, that's A1. So they track these pointers as well, up to the point that we get to, again, we get to line 3. So here we capture the information of memory locations as well.
So, why?
So to have more information to debug, find the fault.
Sure. So this is true enough, right? It's more information. More information could be a bad thing, depending on whether or not that information is useful.
The first trace is not capturing the aliasing part. Suppose if there are 2 pointers which is pointing to the same location and that led to a problem, the first trace will not help us debug it. It will be very difficult.
This is potentially true, but we'd be able to see that aliasing happened to some degree because we have the concrete values, right? We've got we have a concrete trace, so we can see whether or not 2 pointers have the same value.
Could it help us to see where else the issue might happen, but we maybe didn't capture it? So when we do all these assignments, maybe we also assign some variable, but it's gonna be used after line 73. So it could be another area where we don't check enough or something.
Potentially. I mean, but both of these answers are not untrue. They're both reasonable, acceptable, true answers for this. It's essentially, at a high level, you can say that the data structures that manage the data sometimes affect what the data is. So let's say that you've got a tree, right? And this tree holds your data in a certain pattern, and if you add things to the tree, it might get restructured or something along those lines. And so these pointer values that occur inside the tree will affect the underlying structure of the tree, and then will affect maybe what value you read from the tree in the future, potentially. And so one of these captures the idea that the structures that hold the data affect its meaning, and one captures the notion that the values of the data alone are relevant. So if the structure of the tree, for instance, was where the bug existed, then you wouldn't necessarily be able to capture that with the first trace. The distinction between those two, I think, isn't all that clear in the paper.
They did mention something about vector plus length.
Yeah.
Where they say that if you don't put that over there, then it will get optimized out. You will not get that in the final case.
Yeah, but they don't necessarily say to a significantly motivating degree why that matters, I think. But yeah, they have it there for completeness, but it's not quite as in-depth as you'd expect for a full conference paper often.
Yeah. So they call these two abstract slices, which one of them is address insensitive, the other one is address sensitive. So if we go back to here, then what they want to do is, it's called aesthetic fault abstraction with error invariance. So first we want to know what are the error invariants, right? So if we come back here, the green lines are the error invariants, right? So they have two properties. They capture, so for example, assume we are talking about I1, right? So what happens here, if we run the program to the end of line 3, the concrete values will satisfy I1, right? And then if we execute it further, any execution that satisfies this invariant will also get into the assertion, the fault, right? Will capture it. So these are the two properties of the error invariance. So they're going to use these properties to put the information that are irrelevant away, right? So what they say is, my interpretation is that, so they say, first of all, where does this error invariance come from? So what happens is that they give the error trace to the SMT solver, and the solver gives us these error invariants. So, what I think is that they will, after that, they will go through the invariants and see, for example, line 3 and line 4, for example, had the same error invariant. So we can throw out line 4 because it does not give us any more information. That's how they do the slice out, right? That's how they reduce the error trace to these abstract slices. So one important thing that we want to think about it for now is that how do we tell solver to capture information in regards to address sensitivity? How do we tell it, like, whether pointers are important for us or not? We will answer this question later in the lecture, but it's important to see what's going on here and have it in mind. So
could you maybe write the formula that shows what these error invariants are doing? So we can kind of think about that a little bit.
What they're doing? What do you mean by that?
Well, I think it might be good if we try to step back and get a picture of, okay, we have this notion of a high-level notion of what an error invariant is. If we can see it as a condition, maybe we can think about what it means a little bit more too. Because it's a subtle issue.
As a condition?
Yes, so they've got, where is that?
What can you?
They have the logical formulation in their definition of what an error invariant is.
Oh, okay.
Where is that?
That's in preliminaries. What page is this? The preliminaries on page 5.
Sure. So. So again, we have the error trace, right? And we get the formula. As we talked about it before, it's conjunction of some conditions, right? So T1 and T2 up to some Tn. So if we want to capture the two properties of the invariance that we mentioned before in kind of a formal thing, will be like the first property up to the, if we execute the program up to the last invariant, error invariant that we are talking about, for example, say number k, right? This will satisfy error invariant k. And then we talk about that anything after this will also get into the segmentation fault. No, not segmentation fault, but the assertion. So it's like AK and EK plus 1 up to the end will give us the error.
Sure.
What's the purpose of number 2?
That's kind of what I want to get to. That's where this is subtle, what this is actually meaning. Both of them are kind of subtle, actually.
Well, I can understand the first one, okay, this is how we got to the error. But the second one is like, this is...
It's not just that.
Second one says that if you have total j statements and k is less than j, and the first one says that if the error invariant that first statement and the k statement is same, then you can essentially replace the whole text with just one condition ik, and it will still satisfy the second equation. So if you put from t1 to tn, it is the error, actual error, right? All the error conditions from all the statements.
Yeah.
What they are saying is, using the first one, you can replace the first k and put just one condition over there. Like, you just put that statement over there, none yourself, and it will still satisfy the error condition.
Let's think about this in a different way by thinking about what it would mean to rewrite this formula. And I think that will help make it clearer what's going on. Because I know that essentially everybody, when we've encountered a formula so far, has kind of groaned and said, oh no. So I think it's good to try and dig into this a little bit and reason about what these formulas mean so that you can work through them more on your own. So let's just consider something that seems like it would be a simplification of this, right? The base formula is just t1 and ... through tn implies false, right? Because the correctness assertion is unsatisfiable, right? So how is this different than that?
It's the same thing.
It isn't.
Almost.
Almost, but the how they are different is exactly the issue of what makes it useful.
Is the reason why the path from the start of the program, if you just went from start to end, there's paths that would avoid the error.
We're only considering one path, right? We're looking at a concrete trace.
Oh, you're right.
And not only that, our inputs are fixed.
Yeah, there is actually only one path.
Yeah, there's only one path. There's only one possible behavior because our inputs are set. So everything is concrete and deterministic.
So I think they are kind of making a summary of what has happened up to now, and we can only have this and continue.
This is true. This is true. But it's when we have a summary, what is the notion? What does that mean? If we say we've got a summary of something.
It means we can just take it and continue.
Sure, this is true, but it's not just that, because if the summary is as complex as the prefix, then we haven't gained anything, right?
Yeah. It's like a general thing, kind of.
Okay, it's an abstraction. Once more, we're dealing with these notions of abstractions, and an abstraction is just a group of stuff. But the idea is you group some of the things together, and you throw the irrelevant things away. So if we look at this t1 and ... tk implies ik, and ik and these other things imply the failure.
That's the abstraction.
This is part of the abstraction. Maybe it's the case that we can take out some t in between t1 and tk, and it will still imply ik. So you can remove some conjunct in the preconditions of 1 and still imply ik, right? This captures a semantic notion of slicing. Remember, slicing is the idea that we can remove things that are irrelevant to the failure. This is just a logical way of expressing that.
That's fine. What about number 2? Why do we have it?
Because you still want to actually cause the failure, right? So what we're saying is that we can summarize the prefix of the trace, potentially removing some of those steps. And even if we remove some of those conjuncts, even if we remove some of those steps in that first part of the trace, we can still cause the failure with the suffix.
Yes.
Yeah, I think it will be more clear if we go through the algorithm and we will see how they actually
Yeah,
work.
it'll be clearer once it plays out, but I think capturing this logical notion is good,
But
at the very least.
the second part of it isn't used other than completeness, saying that.
Well, the first part of the trace may prove something that doesn't guarantee the failure too. Right? Maybe the first part of the trace can prove that x equals 5, but x has no relationship to the failure. Great. What does that give you?
Yeah, and so you remove.
Not necessarily.
Right. Anyway.
Right? The question is that you want to have a summary that can still prove the failure, and that's what the second part gives you. And you want this summary to be potentially simpler than just having the entire prefix of the trace, which is what the first condition gives you.
All right.
And that's what makes them to split the error trace.
Yeah. Well, this is one notion of splitting. There's a separate notion of splitting that we'll encounter. But let's move on then to the stuff that you actually want to discuss, and we'll see what.
Yeah, so the question here is that this algorithm that we talked about seems good, right? It slides out like irrelevant things. So what's the problem with it that we don't actually use it and we are looking for something more? Can anybody think of something? What's the challenges with this algorithm slicing out stuff?
Which I've pretty much forced you to erase in order to write this other example.
The solver may not be able to solve it because the trace is so huge. It gets complex at each stage.
Yeah, that's one reason, true. Yeah, what else? So actually what we can think of is that what if we have like some codes that we don't have access to, like library function calls, or and also this algorithm doesn't capture a good memory algorithm, like it is not actually handling pointers and stuff that okay, let's come here. So the first point, large error traces that we mentioned. So the contribution here is that we are going to have the subtraces, and we need a precise memory model. Also call to the library functions and nonlinear arithmetic expressions. Also, we're going to deal with that as well. So let's go back here. So what we have now, we generated the error trace. We are going to analyze it, and we talked about the static fault abstraction with error invariance. And we talked about the challenges as well. So now we're going to talk about how do we split the trace, and then talk about how do we do the pointer elimination, right? So let's go to the actual algorithm that they have here. I don't want to erase the stuff we may need them, but okay, let's see. So as you see in the input, we have a program and input, right, which fails the program. So we have this program P, and then we give it the input, and as we talked about before, they have this instrumentation stuff that gives us an executable file. So in the next step, we will have the executable error trace, right? And which is the line create trace, right? So then they have this function create breakpoints, which we haven't talked about it yet. So that's the way they try to do the subtracing, right? So they say whenever we have a function call or we have a return statement, we put a breakpoint there, right? So in the next step, we have these breakpoints on the error trace from like E1, EM minus 1, and EM, right? Yeah, that's what create breakpoints does. So then their main algorithm is this for loop, right? So they have a for loop that comes from that comes backward kinda from the second last breakpoint and it goes up, right? So let's go through the iteration. First iteration, right? So it will be from m minus 1, which is here. So the last one, as we can guess, is the actual y, right? It is the assertion, actually. That's why we don't start here. So what is bm minus 1? It is actually the call side that caused the assertion, right? As you remember here, it was research. So we have a call to research here. Yeah, so we are actually going to see what has happened in this subtrace. So, okay. First function we see is get the concrete state. What does it do? It actually tries to execute this error trace up to this breakpoint. And then we will have all the values captured, right? We will know which variable has which value, what pointer points to what location, and we have all that information. And okay, so what we need to know here is that so what are they trying to do? We are making this subtrace and we want to give it to solver. So what do we need now? Remember, the solver gets an error trace formula. So now we need to make one. So remember, error trace formula consisted of 3 parts: the initialization, the conditions, and the assertion. So they are trying to make all these 3 parts separately, right? So that's why they have st in it, which is all the concrete values we have up to here. They put them all together, and it will be our first part in it, right? And then they'll have this st post, which is kind of it is going to be the assertion. But for the first iteration, for now it is just true, right? Because last invariant was initialized to false, as we see there, and not of false will be true. Okay, so in the first iteration, nothing particular will happen for this. Then, so we want to see what will happen to the main thing, the conditions here. They use this function extract subtrace, which gets the whole trace and 2 breakpoints and tells us which instructions were executed, right? So we can put them all together and make the error trace formula. Now we are ready to give it to the solver, right? And it is smaller, so we have kind of improved the performance. And so they give it to the solver, and remember what did the solver do? It gives us the error invariance, right? So they are from I0 to ik plus 1. Okay, that's now we can see why we're here talking about this summary thing. They will set last invariant to I1. So why I1? If we go back to the example here, we'll see, okay, I0 is always true, so we kind of don't want to put that in there. So we'll go to I1, right? So I1 is kind of a summary of what has happened till now. So if we have the negation of it, it is kind of play a role as our next assertion. You know, so like when we wanna execute the program for the upper portion, we can use the negation of this error invariant as the assertion. It summarizes what has happened down there. It means if you can't satisfy this, it means, yeah, you will get to the error anyways. So I'm not sure if there's questions with that.
Is that relatively clear? The idea is that you're finding the invariant for the first part of this subtrace, and you can just use that as your assertion for the next step backward. Everybody, okay.
Okay, good. So go back to the algorithm. Okay, so all good, right? So here, final step, abstract slice. We slice out everything that is invariant, right? We'll go through them and see, okay, what error invariant is implying the other one, and all the lines in between slice out, as we talked before. So now we're getting to the question that I mentioned before. How do we tell the solver that we want to care about the address sensitivity? So for more details, we will go to another part, which is error trace construction. So okay, up to now we had this executable error trace. We break it down to smaller fragments. Now we want to do the pointer elimination, which we had to approach for. Okay, let's first go through the address sensitive approach. They say, okay, we will go through all the pointers. For each pointer variable, we will log the memory address that it carries. So for example, say some pointer had the memory location 0x123, right? So next step, for each memory location that we collected in the first step, we create a local variable. So in this case, for example, mem of 1 to 3. So at the final step, we iterate over the executable trace and do the replacement algorithm. How it works, we have example here. So say we have this line, vector.vlangth equal to 0. So we see that here we have this weird condition. If vector plus 8 is equal to memory location 1 to 3, then put the memory variable to 0, right? So the point here is that if we put that if statement there and we turn it to the first order logic, it will give us an implication, right? So that's how we capture the address sensitivity, right?
I see a question. No? Okay, then I saw consternation.
Implication, what is
Implication is like this.
Yeah.
Yeah.
Just if then.
Yeah. So how it works is that so we can so in the error trace formula, right? We have this thing in there. If we didn't consider it, we wouldn't have it. So SMT wouldn't reason about it and wouldn't capture it in the results that it is giving back to us in the error invariance, right?
It's just like we saw with Dart, right? When you take the true branch of something, you add that condition to your path condition. That's all it's doing.
Yes. So at the end we see we captured y vector that we length pointed to the memory location 1 to 3. So let's go to the other one, address insensitive approach. What we have here is like exact same thing. The only difference is that we didn't put the if statement here. So all the same, just don't put the if statement, you will not capture that information.
Are people comfortable with the idea that we can take the trace and see which statements are executed to make this other program as well? So we can create an executable trace? Okay, good.
Good. Okay. What's next? So we are going to the evaluation part. So they had the experiment with two programs, SIT and GZIP, and they have all the information they got in this table, right? So as we see, the whole program was the first line. We can see line of code, right? It's huge. Then they did the instrumentation and they ran it again, and they saw that okay, it has like slowed down the program 5 times, and then they said okay, the log size was okay, tens of kilobytes, so it is good, it's not that big. And then they said okay, line of code for trace executable code was still around 1,000 that we saw before, right, at the beginning. And then they try to slice out the stuff. So what we see in lines 6 and 7 is a slicing out results with address sensitive approach and address insensitive approach. So what we want to think about here is that why in the set program there is a huge difference, but in GZIP we don't have actually a big difference, only 2 lines. Can anybody think of any reason for that?
They're very similar, either sensitive and address insensitive.
Yeah.
It's just that happened. This piece of code that in this trace executable file that was there, not very different.
So the question would be why?
Why?
Not many if statements.
Pointers.
Yeah, true.
So essentially you can think about it that one of them deals with data structures, or pointers, but data structures, and the other one just doesn't really have any data structures to deal with.
It doesn't really matter if you include that information to just has 2 more lines, right? Okay.
What do people think about this? This is probably the last slide we're actually going to get to. So what do people think about this?
Test cases that ran in 4 to 5 milliseconds.
Yeah.
Exactly, real world, large scale.
Yeah, so their big claim here is scalability to real world things. And they've taken a system that worked only on intra-procedural small functions basically before, maybe 30 lines of code, and scaled it up to something that can run on 1,000 step traces. Real world executions might have millions of instructions, or billions, or more.
Yeah. And it's actually something weird is here is that they said for, I don't remember which one, but they said they only had a 2 partition thing.
Mhm.
So they didn't actually use the breakpoints for function calls and return
They
statements.
got out of memory.
But
That out of memory errors.
No, no, no.
It
For
appears
their
that
own
that was related
approach.
to using different versions of their SNT solver, which is more an implementation issue, I think.
Okay.
But they claim scalability, but they don't really demonstrate it. They demonstrate better scalability than previous approaches, but 1,000 statement traces are still very, very tiny.
Yeah. True.
Is it possible that the traces would be larger than the program?
Absolutely, loop, right?
Yeah.
Yeah. So that's entirely reasonable, and in fact, that's usually the case. Because again, that's why you'll have millions and billions of instructions easily in a trace, even for a short real-world trace. The other thing is, what's the nature of these bugs?
Point segmentation faults.
They're segmentation faults. So was the first one. In the debugging research community, it's actually well known that crashing bugs are easy. They have few constraints in general, and they're usually easy to solve. So they're not really looking at the tough sorts of bugs that we don't already have techniques for dealing with. Now, are there any other issues with their evaluation? As we've run out of time, but I think there's a few other things we want to.
Like, I probably should have read in this one. Bug assist. What is that?
That was one of the techniques described at the beginning, where you look for what constraints you can remove from program in order to have the program generate satisfy the preference condition essentially.
Can we also talk about the comparing with other?
That's the big one, I think.
Okay, then we have the nexus list.
Okay, well, this actually isn't the big thing to me. Their comparison to here is kind of not that great, I think.
Yeah.
So the dynamic fault localization, one, they don't really characterize recent dynamic fault localization systems. I say this as someone who's written something that would be comparable with their technique, but works dynamically, and generates explanations as well for bugs, which is, unfortunately they didn't cite it because I actually talked to Martin about it back in 2012. But that's an aside. What about slicing?
Yeah.
What about just applying slicing? For these bugs, slicing should work wonders. And what's more, there's a technique called thin slicing, which is slicing but ignore the data structures, which will give you the exact same results as their pointer insensitive approach. And it's efficient statically. And that's because they're looking at crashing bugs too. And crashing bugs are a bit easier to diagnose that way.
So, did they do anything?
This is a big advancement over the previous error invariance approaches, but it's still not realistic. And they don't do, I would say, an honest comparison with the existing techniques for explanation generation that are either dynamic or static. I don't think that they have a clear picture of what their related work actually is, and that makes it hard for them to list out their contributions in an accurate fashion. So that's one of the reasons why this is in a second tier or third tier conference instead of a higher tier conference.
No scam conference?
Scam is a legitimate conference. I mean, it's a legitimate conference, but the name aside, there are some flaws in the presentation of this paper that they don't address. And if you're part of the debugging community, you go through this and you realize there are shortcomings that would need to be addressed before this technique is applicable to real world code, as opposed to this intermediate step between completely fake and kind of fake.
Yeah, but I think the contribution that made these softwares were pretty good. We didn't have it before.
I agree. I think their contributions that they made for the error invariant system are actually good and they're cool. And they use some of the same techniques that I used in the paper that I published before them that they didn't cite. Which is unfortunate from my perspective. But it tells us that some of these underlying optimizations are kind of the right way to go when you're looking at explaining, instead of just hypothesizing where faults might be, explaining how failures occur and explaining what went wrong inside a program. So I think there are some real good trends that we see in this paper and good contributions in this work as well. They don't evaluate it or assess it very well. I guess that's us getting kicked out. So,
thank you.
Yeah. So I will send out again the stuff that I haven't sent out that I said I was going to last time. But if somebody does want to present next Thursday, we'll have another paper that isn't quite as opaque as the one we looked at.